In this video, we will work with contingency tables, or contingency matrices as they're often termed. Contingency table and contingency matrix is the same thing. We will first see how to tabulate counts for two variables in one table, and we will talk about indices of association among the two variables that are cross-tabulated, and tests of equality of proportions between the two variables, which are tests of relatedness between the two variables. Our example will use real data from a study on language screening. In this study, there were teachers who completed a checklist called the Children's Communication Checklist, aimed to detect language difficulties. And children were also assessed by clinicians using the clinical evaluation of language fundamentals. This is a well-known assessment test used to detect children with developmental language disorder. In each case, each child is classified as language impaired or not impaired. So based on the teacher checklist, we can have a classification as impaired or not impaired. And based on the clinical evaluation, we also get a classification as language impaired or not impaired. So we can cross-tabulate these two variables so that each child finds itself in one of these four cells. So a child that is classified as language impaired, both by the clinical evaluation and by the teacher checklist, would come to this cell. A child that would be classified as not impaired by the clinical evaluation, but as impaired by the teacher checklist, would be in this cell. And in this study, the actual numbers of children were these. So there were 13 children who were classified as language impaired by both the clinical evaluation and the teacher rating scale. And there were 32 children who were classified as not impaired based on the clinical evaluation, but were classified as impaired on the basis of the teacher checklist. The total number of children that were identified as impaired by the teacher checklist is 13 plus 32 is 45. Accordingly, the total number of children that were classified as not impaired on the basis of the teacher checklist was 124. We can do the same for the columns. So there were 32 children that were classified as language impaired based on the clinical evaluation, and 117 children classified as not impaired in total based on the clinical evaluation. And the grand total is the overall sum of cases. So there were 149 children in total. How well did the teacher checklists agree with the results of the clinical evaluation? The teacher ratings agreed with the evaluation for 13 children. They both classified as language impaired, and for 85 children, they both classified as not impaired. They disagreed for the children that only one of the two instruments classified as language impaired. So the total agreement is the sum of these two numbers divided by the grand total. So 13 plus 85 divided over 149 is 66%. Teachers' ratings and the results of the clinical evaluation agreed for 2/3 of the children. We can formulate this problem as a question of equality of proportions. What does this mean? Look at the proportion of children classified by the teacher checklist as impaired versus not impaired in each case. For children who were deemed to be language impaired in the clinical evaluation, the teacher checklist resulted in more children being classified as non-impaired than impaired. For the children deemed to be not impaired by the clinical evaluation, the teacher ratings resulted again in more children classified as non-impaired than impaired. So in both cases, the teachers classified more children as non-impaired than impaired. This makes a lot of sense in the general population, but when we look at just the children who are deemed to be language impaired by a relevant clinical evaluation, then we would have expected this proportion to be very different. If the teacher checklist was actually working as we wanted it to be working, if the teachers were doing a good job in screening children who might be language impaired, then we should see here a higher proportion of children deemed impaired on the basis of the checklist than deemed non-impaired, because this column lists the children who are impaired according to the clinical evaluation. In contrast, we see that the proportions of children are both less than 1. So 13 over 19 is 0.68. 32 over 85 is 0.38. It's good that this proportion is higher than this proportion because it suggests that there is a higher proportion of children in the clinically designated impaired category that are rated to be impaired by the teacher checklists than the proportion of children in the non-impaired category according to the clinical evaluation, as it should be. So this number should be a big one, and this should be a big one if the two kinds of assessments agreed well. That would lead to very different proportions. If, on the other hand, the teacher checklists were irrelevant or the teachers were unable to make the correct judgments, then we would not expect these proportions to differ. Imagine, as an extreme example, that the teachers were completing a checklist about something completely independent, that they weren't rating anything related to children's language. Then we wouldn't expect the ratings of the teachers to be in agreement with the results of the clinical evaluation of language. We would expect these proportions to be equal if the two variables weren't related. So a way to test whether it seems that the teacher ratings are reliably associated with the clinical evaluation is to test whether these proportions differ from even proportions. In other words, we need to run a test of equality of proportions based on these observed counts. And to do that, we need to derive some expected values. Note that all the marginal sums are fixed and cannot change. We cannot change the fact that there were 149 children in total. We cannot change the fact that teacher ratings resulted in 45 classified as language impaired and 104 classified as non-impaired. And we cannot change the fact that the clinical evaluation resulted in 32 classified as language impaired and 117 as non-impaired. Still, we want to derive expected values based on the assumption from the null hypothesis that the proportions are equal, which amounts to the assumption that the two variables, namely the language evaluation by the clinical screening test and the teacher rating checklist, so these two variables are unrelated. The null hypothesis says that this and this, the self and the CCC, are unrelated. That's our null hypothesis. We're hoping they're not unrelated, that teacher ratings are related to self results. In other words, that teacher ratings are useful indicators that can be used as early screening. And to be able to conclude that, we must be able to reject the null hypothesis that the two variables are unrelated, which is the same as the statement that the proportions are equal. When I talk about equal proportions in a 2x2 table like this one with 4 values, so we have 4 cells, 4 values, to say equal proportions, which amounts to no relationship between the two variables, this means that the proportions are going to be equal over both rows and columns. So this over this should be equal to this over this. That's the first line. As well as this over this should be equal to this over this. That's the second line. That's because if the two variables are unrelated, the relative proportions will be the same. If the row variable and the column variable are not related, there will be an equal proportion of the second row over the first in the two columns, and an equal proportion of the second column over the first over the two rows. How are we going to derive these expected values? This is the trick that produces the correct values. Let's say we need the expected value for this cell. So how many children would we have expected to be classified as language impaired by both instruments? So to be classified in the first column and the first row, if there were no differences in proportions over the categories of these two variables. To find that, we look to the marginal sums for the cell we're interested in. So for this cell, the row marginal sum is the total number of children classified as impaired by teachers, 45, and the total number of children classified as language impaired by the clinical evaluation, which is 32. We multiply these two, and then we divide by the grand total. And the number is 9.66. This is our expected value for the number of children that should be in this cell, given these marginal sums and the assumption of equal proportions. We retain the decimal number in the expected proportions for all calculations. Likewise, to find what the expected value for this cell is, we look up the relevant marginal sums, we multiply them, and then we divide by the grand total, and we come up with a value of 35.34. That should then go there, and then we do the same for the other two, and these are our expected values. Let us confirm that these values indeed have the desired properties. If we divide this number by this number, the result is 0.27. If we divide this number by this number, the result is again 0.27. So we have equal proportions between columns in the two rows. What about in the other direction? If we divide this number by this number, the result is 0.43. If we divide this number by this number, the result is again 0.43. So we have equal proportions of rows over the two columns. Moreover, if we add these two numbers, the result is 45, equal to the corresponding marginal sum. If we add these two numbers, the result is 104. If we add these two numbers, the result is 32. And if we add these two numbers, the result is 170. So these values exhibit the necessary property of equal proportions across both rows and columns while conserving the marginal sums. So these are the right values to use for the expectation coming from the null hypothesis that the proportions are equal for this sample size. We can now go on to our familiar table to calculate our index of proportion inequality. We just list the 4 cells as if they were independent categories because each child can only be in one of them. These are the observed counts. These are the expected counts. We subtract the expected from the observed, and we multiply these numbers by themselves and divide by the corresponding expectation. So this divided by this results in this number. And this divided by this results in this number, and so on. And we add all these up, and the result is 2.1. This is our chi-square. The value of chi-square for this table, for this contingency matrix, is 2.1. Before we can look up a probability for this number, we need to find out how many degrees of freedom we have. How many degrees of freedom does a 2 by 2 matrix have? Let us imagine that one value changes. So let's say that 13 was actually 14. The sums cannot change, neither the total nor any of the marginal sums that tell us how many children were classified in each category by each variable separately. So this sum constrains this count to be 31 in response to this one becoming 14. Likewise, this sum constrains this number to be lower as well. And then these sums must also constrain this count to be higher in order for every marginal sum to hold. Thus, by changing only one value, every other value was constrained. We only have 1 degree of freedom. This makes sense because there are 2 categories in the columns. So 1 degree of freedom this way, and there are 2 categories in the rows, so 1 degree of freedom this way. So if we multiply 1 by 1, there's still just 1. And there is 1 degree of freedom in total for the whole 2 by 2 matrix. Using these numbers and going on to the p-value calculator, we can select the chi-square distribution with 1 degree of freedom and enter the value we have calculated, that 2.1, and we see that the p-value is 0.147. For the chi-square distribution with 1 degree of freedom, the value of 2.1 is associated with a probability of 0.147. This means that the probability of obtaining a chi-square value greater than or equal to 2.1 in samples drawn from two variable populations with even proportions of two categories in each variable, so even proportions over the whole 2 by 2 matrix, the probability of getting a chi-square greater than or equal to 2.1 is 14.7. That's a relatively high probability. It's certainly much higher than our convention of 5%. Therefore, we cannot reject the null hypothesis. The association between the two variables is not statistically significant. This means that the observed proportions are not statistically distinguishable from equal proportions. Equal proportions means unrelated variables. So sampling randomly from a population with two variables that were just unrelated could have produced a result like the one we observed. And the relevant conclusion for our study is that teacher ratings are not systematically related to screening results. It's consistent with the possibility that teacher ratings were not related to the results of the clinical evaluation. Now, this does not mean that the teacher ratings in the study were not related to the language evaluation. It means that if they weren't related at all, we could have gotten a count like the one we did. So we do not have strong evidence to conclude that teacher ratings are systematically related to the language evaluation. This could be because the checklist is not a very good one for some reason, or because teachers are unable to judge what needs to be judged when it comes to language development, or both. The overall conclusion is that based on the counts we observed, we cannot conclude that teacher ratings of this sort can be considered to be a useful screening approach for detecting children with possible developmental language disorder, as that is typically determined with a clinical evaluation like the test that was administered. So that was an example with a 2 by 2 matrix. So each variable could only take two values. What if there are more possibilities? What if there are more categories? The general process is the same. Let us look at an example. Let us look at the question whether high school completion rates are associated with parental education. We will use data on high school students for the years 2013 to 2018 as downloaded from ssb.no, focusing on two variables. One variable will hold either a yes or a no, so completed high school versus did not complete high school. And the other variable will be the level of parental education, here broken down into just 4 levels. So each youth is classified according to these two variables in one of these cells. Down the rows, we see parental education, so 4 levels of parental education. And over the columns, we have the two categories related to completion. Completed the high school versus not completed. And these are the totals. We're talking about 29,000 high school students who either completed or did not complete their studies. It looks like there is a much lower proportion of completion for students with parents with lower levels of education as compared with students having parents with higher levels of education. So here, the great majority complete their study, whereas here only a minority complete their study. And there is a gradual change as we go down the rows. So is there a statistically reliable difference in proportions here? Or is this consistent with random sampling from two categories with even proportions? what would even proportions be in this case? It would be that the proportion of students completing versus not completing would be equal across the 4 levels of parental education. It would also mean that the relative proportions of parental education would be the same for students completing the study and students not completing. So these two go together. If you have equal proportions this way, you also have equal proportions this way. We can use our trick with the marginal totals to compute the expected values. So if you multiply this number by this number and divide by this number, you come up with the expected value for this cell, and so on. And this leads to a value of chi-square equal to 788.5. This is a truly huge value that indicates that the difference in proportions is very reliable and unlikely to have arisen from sampling from the null hypothesis, from a population with equal proportions. The number of degrees of freedom for checking this probability will be derived by considering the number of categories in each direction. So going down the columns, there are 4 categories, 4 different rows in each column. This means we have 3 degrees of freedom over the 4 rows. And going right on a row, we see that over the 2 columns, we have 1 degree of freedom. So 3 times 1, number of rows minus 1, times number of columns minus 1. The product of the row degrees of freedom and column degrees of freedom is 3. So for 3 degrees of freedom, if we look up that chi-square value, we will see that the probability is so small that it cannot even be represented in the computer. This means that these data are not consistent with random sampling from a population with equal proportions. It is extremely unlikely to get such numbers from equal proportions. We can safely conclude that the variables high school completion rates and parental education are associated. We can safely conclude that there is a relationship between parental education and study completion. This relative certainty in this conclusion doesn't tell us how much we would be able to guess one from the other. So our confidence in the fact that there is a relationship is different from an assessment of how strong this relationship is. To find out how much we can derive or guess one variable from the other, we will have to compute an index of association. Before we move on, try to think about guessing. Obviously, if you know that someone's parents only finished elementary school, you should guess that they will not complete their high school, and you will be correct more often than not, although the difference would not be very large. If you know that someone's parents have had long higher education, you should guess that this person completed high school, and you will be correct more often than not with a somewhat higher rate. How big is this difference depends on the actual numbers and the sample size. And there are a number of indices of association that quantify these relationships. The indices of association we see most often, which are quite useful for this purpose, are phi, and this is the formula for the 2x2 case only, and Kramer's V with the corresponding formula. Note that in the 2x2 case, these two are equal. K here refers to the smallest of the two dimensions. So the dimension or the variable with the fewest categories. So in the 2x2 case, K is equal to 2. 2 minus 1 is 1. So this goes away and you have the same formula, except that phi also takes a sign to indicate the direction. These indices of association are very useful because they're interpretable. They range from 0 to 1. 0 means no association. No association means equal proportions, and it also means you cannot predict one variable from the other. Knowing the value on one of the variables does not help you guess the other variable with any increased success. They range up to the value of 1, which is the highest possible value, to indicate a perfect association. An association equal to 1 means that you only need to know one of the two variables because you can perfectly predict the other one from it. This is essentially never achieved in practice, and it means that the two variables are in perfect agreement. These values are thus functioning like correlation coefficients in the sense of allowing you to judge the strength of an association between 0 and 1. Actually, phi goes all the way down to -1 to indicate a strong association in the opposite direction. So phi distinguishes between positive and negative associations, whereas Kramer's V doesn't. Having positive versus negative associations is questionable at best when you have a nominal scale, but is interpretable when you have an ordinal scale. These indices are interpretable regardless of the number of categories and regardless of the sample size. They're always interpretable in the same sense between the 0 and 1. This is very useful. This is not true of chi-square. Let us look at the values of these indices for our two examples. For the language screening example, phi equals V equals 0.12. So the two indices of association for the relationship between the variables teacher checklist and clinical evaluation of language development, these two variables are only associated to a very low level of 0.12. For our high school completion versus parental education example, Kramer's V provides a value of 0.16. So it is still a rather low association, which is consistent with the fact that you cannot predict very well if a student will or will not finish high school just by knowing their parents' education level. You can only make an improved guess, but you will be quite often incorrect. The important thing to note here is that these two values are in fact quite similar. So the strength of the association in the sense of how well you can predict one variable from the other given the observed counts is relatively similar. There is a very small difference. It's not a substantial difference. However, the results of the chi-square test of proportions were very different. Indeed, in the language screening example, we could not reject the null assumption that the two variables are unrelated. The data that were observed were consistent with the hypothesis that the data were randomly sampled, that teacher screening checklists were unrelated to the clinical evaluation classifications. This is not an encouraging result for using these teacher checklists. In contrast, having a huge sample size led us to reject with very high confidence the null hypothesis when it comes to the relationship between parental education and high school completion. Although our ability to predict one from the other is still relatively low, we are quite confident in the relationship, even though it is a weak one. To sum up, contingency tables or contingency matrices refer to cross-tabulating cases across two categorical variables. Each case, so each person in these two examples, can only belong to one of the cells because it corresponds to one combination of measurements, one value on one variable and one value on the other variable. So the cross-tabulation results in a table that's called a contingency table or contingency matrix. If the variables are not related, then the proportions of classification on one variable will not be associated with classification on the other variable. So the proportions will be even across levels of the other variable. Therefore, an association between the two variables is indicated by uneven proportions in the levels of one variable across levels of the other variable. Uneven proportions means relationship between the variables, means ability to predict one from the other to some extent. The association indices Kramer's V and phi index this association strength. They essentially answer the question, how far from equal proportions are my observations? The chi-square test of proportions answers a very different question. The question that chi-square test answers is, are my observations consistent with sampling from equal proportions? It's important to realize this is a very different question. And the difference between these two questions depends mostly on sample size. So if you have a small sample, it is possible to have very unequal proportions and still be consistent with sampling from equal proportions. So extreme samples, non-representative samples, are more likely when they're small. We've seen that in every kind of example so far, starting with coin flips and going through sample from distributions such as the normal distribution and the sampling distributions of statistics. In contrast, having a very large sample allows you to exclude the possibility of the null hypothesis even when you're not very far from equal proportions, because you have a more stable estimate of the proportions in the population. In other words, the chi-square test fits the table of observed proportions against the table of expected proportions, that is, equal proportions under the null hypothesis assumption. And in the end, provides us an index of association reliability in the sense that we can look up the probability that such an index could have arisen by random sampling from equal proportions.